Boby, what is this now?
This is a nice picture I've seen. I thought I'll show it to you. So, I mean, looks like some. It's not. I don't know what it is. It's not heat sink.
No, it looks like
Heat sink had some fins.
fins. Yeah, that's true.
So also kept in 90 degrees.
And also, it's on a PCB that's like long and thin.
Yeah.
Which is weird. I mean, the only thing I can think of it is, remember when we did the coil-based sensors, they were in different directions to measure different axes.
Magnetic field, no?
Yeah, magnetic field.
Yeah, but this may not be that, no? Because this one looks like a metal cover.
Yeah, no, what I'm saying is maybe it's somehow something is measuring two different axes.
Ah, okay.
I don't know. I'm just thinking because it looks at the same, but it's 90 degrees.
I think you are very close to it. What about this? We don't know. Only if you search for the data sheet, you will come to know.
Yeah, again, it's got very good packaging.
Yeah, correct. Actually, you know, this in your cell phone, etc., it shows the acceleration.
Yes.
Correct.
Yes.
How is it sensing?
There must be some sensor
There
that
must be
measures
something. Yeah.
acceleration.
So, see, when we discussed the piezo, we were talking about spring mass damper model
Yes.
for a mechanical system.
Correct.
So, if I have, let's say, something like this, and let's say there's a cantilever and a mass.
Okay.
And this housing is exposed to movements.
Okay.
What will happen to this mass?
It will move according to the
Yes.
force given to the
Yeah,
mass.
yeah. So basically what you are saying is there is F is equal to ma.
Yes.
Correct?
Correct.
So that means if the mass is known, right, and this whole thing is exposed to some acceleration,
Right.
if I can measure this force, then I will come to know what the acceleration is.
Correct.
Correct?
Yes.
Now, how will I measure force? We can measure in different ways. I mean, one thing long back we discussed, we can use strain gauges here.
Yes.
Now we know various mechanisms.
Right.
So it could be, you know, we may have some arrangement here as a secondary detection that looks at maybe change in capacitance, or this strip may be made of piezoelectric material.
Yes.
That gives an output as it moves.
Oh yeah.
So there are multiple options that we have.
Right. Because cantilever structure you already covered in detail.
Yeah.
So that structure then can be used with different types of sensing principles.
Yes.
Why can we use a piezoelectric?
Piezoelectric can be used.
Yeah.
Yeah. Yeah.
So in this case, the mass will be a mass, but that strip will be. How would that work?
So actually the strip will be very thin compared to the mass at the tip that you have.
Okay.
So you can almost consider the mass at the tip as the mass of the, you know, for the frequency calculations.
Okay. Okay.
So when you have a structure like this, right? Let's say this is fitted on your car or something. So if car undergoes some bumps, your mass will be moving at a certain frequency.
Yes.
Correct.
Correct.
So how do you model that? I mean, it's a mass spring mass damper model, something like this, where the mass is undergoing, I mean, is experiencing, or you are applying some force to the mass.
Yes.
And you look at what's the displacement the mass has undergone.
Right.
So if you know this, you will be able to find out
the force.
Force.
Yes.
If you know the force, mass is known, you will be able to find out acceleration.
Yes.
It's as straightforward as that.
Okay.
I mean, I don't want to elaborate more. Students know the equation relating to this, force and acceleration. But the other point is, if you know acceleration, we also know if you integrate once, you will get the velocity. And if you integrate once again,
Distance.
you will get the distance.
Yes.
In fact, that is one way to measure displacement. Let's say you have a flight going from here to somewhere,
Right.
or you are going to the moon.
Right.
This is one way to measure displacement.
Right.
But I also heard that this is sensitive to, I mean, output is sensitive to serious, some issues like, you are doing integration.
Yes.
So that means if there is some small error in between, you will be keep integrating throughout.
Oh, that's true. Yeah.
Correct?
Yeah.
So the output will have some effect due to errors associated with this, but there are some mechanisms to reduce that also. Right? So the point is, if you have some mass which is on a structure like this, we will be able to measure acceleration. And if you have acceleration, you can derive the other quantities also.
Right.
Now the question is, how do you measure this displacement of the mass?
Yes.
Look at this. Yeah. So let's say I have a movable mass here that can go up or down, and then I keep another two fixed ones. Okay. Right. So this actually forms a differential capacitance, which we have discussed.
Right.
So the C1 increases, and maybe one is C1 and another one is C2. Right. When C1 increases, then C2 decreases, and vice versa.
But this is more like a dynamic movement, whereas in the flow it's just kind of one way.
Yeah, it can be dynamic or it can be static also, in the sense, let's say this accelerometer is kept like this.
Or free falling.
Or let's say it's just kept on your table. See, you see that there is some spring, etc. here.
Yes.
So due to this mass, definitely this will be closer to the bottom.
Correct. If it's placed on the table.
Yeah.
Yes,
so the C2 will be more and C1 will be less. If you place it the other way, you will see this.
Okay, I see.
In fact, I've seen this is used to measure even angle with respect to, gravity vector.
So, in our phone, right, we can rotate, right?
Yes.
Is that somehow based on this? Or can it be based on?
It can be. It can be.
The rotation.
Yeah. So this value of these capacitors can be used to find out that slow movements. Right. That's possible. Right. But in this case, mainly this is designed to measure the acceleration. Right. So you have this mobile mass. Somehow mechanically, we'll show another figure how it is maintained, and then the movement of the mass. In fact, here we were talking about this mass.
Yes.
Movement of the mass is now measured using an attachment like this and two fixed electrodes.
Oh, I see. Okay.
Right.
Right.
It's like here. Not a great drawing, but let's say you have an extension here, and then you have two other
electrodes,
fixed electrodes. You could measure
differential.
Yeah.
capacity.
In fact, it could be potentiometer also. You can use that.
Oh, yes.
But of course, it will affect your. It will introduce the wiper
So there's friction. Yeah.
Yes. Not the best method, but this could be a method because, this is one thing we didn't explicitly say. There is no friction in this capacity measurement.
It's non-contact.
Yeah. Yes. So when we have done the linear or angular measurements, the moving electrode and the fixed electrodes, they are not touching each other.
Yes.
So there is no friction.
Yes.
So using these capacitors, I will come to know how much movement has happened for the mass. So from there, of course, we can now find out acceleration. Right. Now, see, this drawing, I was saying it is awkward, correct? One side alone.
Right.
The mass will not move like this. It will also have an angle.
Yes.
So a better design is something like this, where you have a mobile mass and you have fins on both sides.
Okay.
Right. So you have a electrode. Fins on this side. You also have a fin. You can have multiple fins, but on both sides.
I'm just trying to figure out, can you have a push-pull arrangement also in this.
So this is actually push-pull arrangement. I mean here, as we discussed, if this is increasing, this will be decreasing.
Correct.
And vice versa.
And the other one also, I think, if it even moves like this.
Yeah. So I think by design, these are less sensitive to that kind of movement.
Right. Okay.
So this is more as the direction shows. It is
Up or down.
It's kind of designed to move in this direction,
Right.
but there will be slight movement for the other direction also if you have acceleration in that direction, but it is kind of restricted.
Right.
It will have some sensitivity, but it will be less compared
So
to.
these arms that you have, those arms can. So how does piezoelectric fit into this?
So
this is capacitive.
This
right?
is capacitive.
This is capacitive.
Yeah. So piezoelectric may not be. We will not be able to fit it to that.
Okay.
So piezoelectric, I would say it is more suitable to fit it on this.
Okay.
So in that case, what I will do is I will have a mass here, and then we will have two cantilevers.
Okay. Piezoelectric cantilevers.
It can be like this. Cross-section view. So these two can be the piezoelectric strips.
Right. They will move up or down.
Yeah. So as you go up or down, there will be voltage generated due to that,
Yes.
and then that you can measure.
But it is not a push-pull configuration though. In this case.
Piezoelectric will not be a push-pull arrangement. Yeah. Piezoelectric, maybe push-pull is not required also.
Right.
So here you have this movable mass and then multiple such fins on both sides, and that movement of the fin is again measured using this fixed fins or fixed electrodes and those capacitance values. Right. So you get multiple what shall we say differential pairs,
Yes.
but all those in one side could be connected in parallel and the other side would be connected in parallel. Finally, you get two C1 and C2s.
Right.
Sorry, one C1 and one
minus
C2. So an actual diagram looks like this,
Oh, this is a real.
or a diagram which is more illustrative, where you have this mass, and then you also see some anchor points.
Yes.
So this mass is anchored using these ones, so it's held by those, right? And then these are the fins that we were talking,
I see.
attached to the mass,
Right.
and these are the electrodes that are present. So you are actually now measuring the capacitance that is present between these two. I mean, there is, if it moves this direction, this capacitance increases and this capacitance decreases. Same thing happens in these locations.
Right.
All those come in parallel, right? Similarly, you get a parallel arrangement this side as well.
Right.
So from these capacitance values, you will be able to say how much movement has happened for this mass.
Right.
Now, if you want to see, this is sensitive to movement in this direction.
Yes.
But as you have seen in the initial photograph,
One was like this, one was like this. Yes.
So for the, I mean, if you want to resolve acceleration and to know its actual direction, you will need the x and y component.
Correct.
So this one is for the vertical direction. It's again the same structure, just rotated by 90 degree.
Right. What about like torsional acceleration?
So how do you sense that?
How would you sense something like
So I think there we use the gyroscope.
that? Oh yeah, gyroscope will measure for sure.
So what you're saying is angular acceleration.
Angular acceleration.
Yeah.
Correct. Yes.
So one thing, I think angular acceleration could be derived from this if you have this.
Several on
Yeah,
the side.
yeah.
Okay.
Yeah.
Okay. that makes sense.
Yeah.
Right. Yeah. So if it's something like this,
Yeah.
then you can have it
Yeah.
on the side.
Yeah.
Then that will make
The other one is I need to cross check, but it could be a design where you have a rotary object with fins like this,
that, okay.
and this is
Right.
free to rotate.
Right.
Yeah. So it has to be mechanically hooked somehow, and when there is an angular acceleration, this mass will have a movement, relative movement. So we will have to measure the capacitance introduced between these fins and the fixed fins, and then that could be one way. Right. So actually, students could read more about this, the gyroscope and accelerometer sensors from, I think it's from, this picture is actually I've taken from Analog Devices website. Right. So it's a brief about accelerometer, how it can be, I mean, what's the, or how it works. Basically, it makes use of this mass spring damper model mechanically, captures this information in terms of displacement of the mass, and how this displacement is sensed using a displacement is sensed. It could be using capacitive or resistive mechanisms
or piezoelectric.
Or piezoelectric. Now, in the case of piezoelectric, do you see some benefit?
You don't have to power it. Do you have to power it?
Maybe, yeah, we may have to power it, but of course we can capture some power.
Yeah,
but then that will become tricky, because when you use that power, you cannot use it probably for sensing.
No.
Because then your sensing information will be lost.
Yes, I'm saying the output is just that output.
It is self-generating.
Self-generated.
I agree. That I agree.
Self-powered sensor.
That I agree. Yeah. Yeah. But still, you have seen there is a charge amplifier and so on that needs to be powered. But but the sensor itself is self-generated.
Right.
Correct. But is there any other benefit? See, I was talking about, the sensor kept on a table, and then this was lower compared to this.
Yes.
And it would give an output just due to the gravity.
Yes.
We may not want that. I will always have this 9.8, right?
Yeah.
Depending on the location, it may vary a bit, but that's not the one I'm looking for, right? Now, if the design is,
piezo,
like this, piezo, you can have that force. It may be bent a bit.
Yeah.
Due to this.
Yeah, it's still zero because it's
because it's a DC static signal.
Yes.
Doesn't give any output.
That's true. That's true.
So you get output only due to the dynamic change.
Right.
So that's one main benefit that you have when we use a piezoelectric based secondary sensing for the accelerometer.
Yes.
But I think that is not that widely used. I think the sensors that we have in the cell phone, etc., I don't think it's a piezoelectric based one.
More capacitive.
Yeah, it's a mostly capacitive based one.
Right. I guess maybe the capacitive material is also quite expensive, I guess. I don't know, but maybe it is.
Yeah, so the capacitive, capacitive actually, as you pointed out, it's easy to fabricate.
Yes.
While integrating piezo into this cantilever structure is relatively complicated compared to a capacitive based sensing mechanism.
Right.
So that kind of make it more expensive and maybe a little bit bulky also. So this is another application in the sense how several sensing mechanisms can be combined to realize something else, which is acceleration that you want to measure.
Yes.
And from this data, if you want, you do other signal processing and get velocity, displacement, and so on.
Yes.
So sensor systems mostly not just sensor element alone.
Yes.
You have sensing element, you have analog signal processing, you also have digital signal processing, all that.
Yes.
We have also seen a brief about piezo as a actuator.
Yes.
We may see more of that in the coming class.
Correct. And interesting because, I mean, if you go back to when we first started, and if you look at all the different sensing principles, it's quite amazing how there are so many ways
Yes.
you can sense things, right?
Yeah.
Quite
This is not something we can capture in a class.
No.
We will need several courses to go through all this material. But I think this gives some overview and some details about certain sensors, which gives confidence to drive further.
Yes, correct.